Okay guys, we're going to continue on today talking about reaction rates. So before I start, please have your Chapter 5 guided notes out, and you're going to need a calculator today. So please have your guided notes and a calculator. So today's lesson, we're going to build on what we learned last time. In the last lesson, we ended by talking about 5 factors that will increase the rate of a chemical reaction. And so we talked about those factors, and those were kind of qualitative factors. We didn't quantify anything really. In today's lesson, we're going to get to the numbers. We're going to look at how reaction rates occur quantitatively. So we're going to put numbers to it. So that's where we're headed today. So let's start with the definition of a rate. A rate is a change in something over a change in time. Let me see if I can explain what I mean by that. So a change in something over a change in time. So first of all, in chemistry and in all science classes, you're going to see, you're going to hear change a lot when we're calculating something. We like to calculate the change. Well, there's a Greek letter delta. It looks like a triangle. I would like you to put this in your notes. Whenever you see this Greek letter delta, this triangle, I want you to think of change. So that equals change. But how do you calculate change? If I asked you to find the change in something, well, you would calculate it this way, and I'd like you to write this in your notes as well. Whenever you see the delta symbol, you calculate it by taking the final state of something, so final minus initial. So the final state in something minus the initial state in something. And so that's how we're going to calculate a rate. For example, if I relate this to something that you're probably familiar with, rate of speed. So if you're in your car and you're going a rate of speed, you would calculate it by taking the change in distance divided by your change in time. And most of us are familiar with our rate of speed, and we determine that here in miles per hour. So mph, miles per hour. Well, what that really means, if we were to calculate your miles per hour, it's a rate, and so we need change in something over a change in time. So our change in something here is miles. Our change in miles divided by per hour, so we're talking about change in hours. And so that's how you would calculate your miles per hour. And it might be that you're going 65 miles per hour. That means you went 65 miles in 1 hour. So that's an example of a rate, and hopefully that helps you kind of familiarize yourself with. We're already familiar with rate of speed, but now let's relate rates to a chemical reaction. We do that with the reaction rate. A reaction rate is the change in concentration of a reactant or a product per unit time. So per unit time. So it's the change in concentration divided by change in time. Our units for reaction rates that we're going to see all chapter, the units are going to be molarity per second. So we measure the concentration of a reactant or a product in terms of its molarity, the number of moles per liter, and we're going to divide its concentration by time. Usually it's going to be in seconds, so it's molarity per second are going to be our units. So the reaction rate will be calculated using this equation. So if we look at it, reaction rate is equal to delta, which means change in. Now when you see these brackets here, these brackets mean concentration. So make a little note by this equation. These bracket signs tell you molarity, which again is a way to tell the concentration. So whenever you see these bracket signs, think molarity. So it's the change in molarity divided by the change in time. Now, we talked about this in the last lesson, but some chemical reactions go very quickly. And so your change in time might be in units of seconds. Some reactions don't happen quite as fast. They might take minutes in order to occur. So your units for time could be in minutes. And also, some chemical reactions take a long time. So even you will see units of time in terms of years. So your units here could be seconds, minutes, or years. But most of the time, they're going to be in seconds or minutes. Okay, so let's look at an actual chemical reaction. Let's look at this one here, where we have 2 moles of nitrogen dioxide. It's decomposing, so this is a decomposition reaction into 2 or more products. So this 2 moles of NO2 decomposes to 2 moles of nitrogen monoxide plus 1 mole of oxygen. Well, if we look at really what is happening in this reaction here, this is our reactant, and we're forming the products. So what's really happening is as NO2 disappears, so our reactant here is going to disappear over time. Well, it's decomposing and it's forming the products. So our products, nitrogen monoxide and oxygen, are going to appear. And so your reactants are going to disappear. Your products are going to appear over time. Now I've got a chart here, a graph here that shows this chemical reaction. So again, this is the same chemical reactions right here, where we have 2 moles of nitrogen dioxide is decomposing to 2 moles of nitrogen monoxide plus 1 mole of oxygen. Whenever you see a graph, and we're going to see a lot of graphs coming up in this chapter, the best place to start is to look at what the axes are reporting. Our y-axis is reporting concentration, which will be in terms of molarity. So you'll see a capital M over here. Our x-axis is reporting time. So this is the beginning of the chemical reaction, and this over here would be the end of the chemical reaction. For concentration, this would be very dilute or 0 concentration, and this up here would be the most concentrated part. So reaction rates can measure a lot of things. We can put it in a graph form like this and actually graph what's happening. So I would like to talk about something. Reaction rates can measure the disappearance of reactants, because our reactant here is going to be forming the product, so it's going to be disappearing. And so that's why you see this green line, which is our reactant, the nitrogen dioxide. You can see the green line has a negative slope, which means its concentration is falling over time, which means that it's disappearing over time. Well, reaction rates can also measure the appearance of products. And so that's why you'll notice here, my products, nitrogen monoxide and oxygen, the slope of their line is positive. So it's rising over time. So both of them are going to have a positive slope, which means that their concentrations are going to increase over time, and so they're appearing. Okay. Also, before I put that up, let me ask you a question and see if you can think about this. Why is nitrogen monoxide's slope, the slope of this blue line, twice as much, has twice the slope as oxygen's, this red line? So why is NO appearing twice as fast as oxygen? And the answer goes back to the chemical equation up here. If you look at the stoichiometry of it, we have 2 moles of nitrogen monoxide forming for every 1 mole of oxygen. And so because nitrogen monoxide is forming at 2 moles for every 1 mole of oxygen, it's forming twice as fast. And so you'll see at the end that the nitrogen monoxide concentration is twice that what oxygen's concentration will be. And so the final thing here, reaction rates are stoichiometrically proportional. So it goes back to the stoichiometry of the balanced chemical equation. Okay, we're going to get into some problems here, but I wanted to just introduce reaction rates with this slide here. We're going to be talking a lot about the slope of lines. Slope. And so hopefully you can remember back to your math class and remember what a slope of a line is. Slope is equal to rise divided by run. Rise over run. So in this case, when we have these concentration versus time graphs, our rise is going to be the concentration. And so our rise is going to be in terms of molarity, and our run is going to be in terms of time, which is in most cases seconds. Again, molarity per second. Also remember that some slopes can be negative, because this green line, it's not rising, it's falling. And so our concentration would have a negative sign, because it's falling. Slopes with a positive, slopes that have lines that have a positive slope will rise as they run, and so your molarity is going to be positive, and time, of course, is always going to be positive. So anyway, I just wanted to introduce what slope is. Okay, what this lesson is mostly about is to calculate the average and the instantaneous rate of a chemical reaction. So let me first introduce the definition. So the average rate is the rate of a reaction over a period of time. So it's the rate of the reaction over a time period. Okay? Let's contrast that to what instantaneous rate is. Instantaneous, like its name implies, is at an instant. So it is the rate of a chemical reaction at a specific moment. If you think about, let's relate this to rate of speed again. So an average rate of speed, if you were to calculate your average rate of speed, maybe you're going on a road trip in your car, well, you would need to take the total distance that you went on your road trip and divide it by the total time. So it's over a time period. It takes into account the whole time period. But if you wanted to calculate your instantaneous rate of speed in your car, how would you do that? Your speed or your rate at a specific moment. And hopefully you're thinking to yourself, at a specific moment, well, you would just need to look down at your speedometer. Maybe at that specific moment you're going 65 miles per hour, and so that would be your instantaneous rate. But would that be your average rate for the whole road trip? Hopefully you're saying no, it's not going to be your average, because that's just at a moment in time. Your average takes into account the whole time period. And because you're going slow at first, you're building up speed, and then you're going to brake at the end, you're going to slow down. Your average speed is going to be much lower than 65 miles per hour. Okay, let's relate this to the chemistry again. An average rate is the rate of the chemical reaction over a period of time. So I've got a graph down here. Again, it's concentration in terms of molarity versus time in terms of seconds. So if I wanted you to calculate the average rate from 0, from this point, to, let's say, 150 seconds, so this point, the average rate would be the change in concentration over change in time, so you would take into account that 150 seconds. And so what you would be doing is calculating the slope of a line between those 2 points. That would be your average rate. Now, if I asked you to calculate the instantaneous rate at, say, for example, 50 seconds, okay, just at that specific moment in time, you're going to calculate the rate at that point. Now, it's very difficult to calculate the slope of a curved line. You would need some calculus to do that, and since that's beyond the scope of this class, here's a quick trick to do that. Since this is a curved line here and we want the slope, what we will do is make a tangent line. A tangent line is a line that touches the curve at that specific spot. And so it's a straight line. Let's see if I can draw a straight line that touches the curve at that point. Okay, and so we will find the slope of this tangent line, and where it touches that curve at that point, that will tell us the rate at that moment in time. So that's where we're headed. I've got a few practice problems, even some example problems to show you. So let's get to the example problems. Okay, so this is an example problem. You don't have this one in your notes, so please follow along as I go through this one, because you will have to do a practice problem just like it on the next slide. Okay, so it says to calculate the average rate of both H2 disappearance, so H2 is disappearing, and HI appearance from 0 to 60 seconds. Okay, before we start, this is the chemical equation for this reaction. We've got hydrogen plus iodine goes to 2 moles of hydrogen iodide. So what we're going to do now is calculate the average rate of H2 disappearance. Because it's a reactant, it's going to disappear. And if you look down here on the key, H2 is this blue line. You'll notice that its concentration is falling over time, so it's disappearing. And HI, hydrogen iodide, is going to appear because it is our product. Its concentration is going to appear over a time period. Okay, now very important. Make sure that you pay attention to the time frame that it wants you to pay attention to. 0 to 60 seconds. So we're going from 0 down here, from this time period, to 60 seconds. So it's not the full reaction. We're going to stop right here at 60 seconds. Okay, I would first like to start by writing the equation for a rate. When we calculate the rate of a reaction, we're going to do it this way. We're going to take the change in concentration, so the change in molarity, over the change in time. In this case, our time is measured in seconds. And so it's going to be, our units are going to be molarity per second. Let's do H2, the disappearance of H2 first. Let's calculate that average rate. So again, H2 is this blue line. So we're starting here at 0, and we're going to 60 seconds. So I'm going to make a dot at each one of those. Okay, now remember, whenever you see this delta symbol, it's final, subtract initial. So final minus initial. So when we're doing the delta of the concentration, let's do the final concentration. My final concentration occurs at the final time point, 60 seconds. So this is where we kind of have to estimate. It looks like it's about halfway between 0.2 and 0.4. So what I'm doing is lining this up. Its concentration here is on the y-axis, so I need a mark right here. So it's going to be 0.3. Now we're going to subtract off the initial concentration, which was at 1 molar. So 1. Now I'm going to divide it by the change in time. My final time was at 60 seconds. So I'm going to put a 60 right there. And my initial time, we started at 0 seconds. Okay, so now we can put a calculator to that and see what the average rate was. So 0.3 minus 1, and then divide it by 60. And so I'm getting this, so it's going to be negative 0.0117. My units are very important. My concentration was in terms of molarity. My time was in terms of seconds. And so the average rate for the disappearance of H2 from 0 to 60 seconds was a negative 0.0117 molar per second. Again, it's negative because my slope would be negative for that time period. Now let's do the appearance of HI. Okay, again, we're going to follow this rate equation. The rate is equal to change in concentration, so I'm going to do the final concentration of HI. Remember that HI on this graph is in the yellow. At 60 seconds, its final concentration would have been 1.4. So 1.4 subtract, my initial concentration happened at 0 seconds, so we're at 0 molar there, divided by the final time was 60, minus the initial time was 0. And so 1.4, if you got a calculator, 1.4 divided by 60 is going to be 0.023. And again, my units, because molarity is on top, is going to be molarity per second. Okay, so that's just a quick example problem of how we would calculate the average rate over a time period. Let's see if we got the answers right. And so we were very close with our H2. They just rounded it up to 8 right there. And for our appearance of HI, we were right on. So we did get it right. Again, I hope you see what we are doing. We are just taking a slope of a line. For example, if we're going to 60 seconds and I try to connect these points here in a straight line, we're just taking the slope of that line. And from 0 to 60 seconds here, if I try to make a straight line, we're just taking the slopes of those lines to find the rate. Okay, practice problem number 1. I would like you guys to try this one on your own. It says to calculate the average rate of both H2 disappearance and HI appearance. Now careful, this one is from 20 seconds to 100 seconds. So the time period has changed. We're going from 20 seconds to 100 seconds. So your final time is going to be at 100. Your initial time is going to be at 20 seconds. So please follow this rate equation. It's equal to the change in molarity, change in concentration, over change in time. So see if you can't do that for both H2 and for HI. Please try that on your own. See if you can get the average rate for those two. Please hit pause. If you're watching the video, please hit pause. Once you have your answer, hit play and see if you got it right. Okay, so hopefully you went ahead and solved for those average rates. And I did too. And so I found the average rate of disappearance for H2 was negative 0.006 molar per second. And the average appearance of HI over that time period was 0.0135 molar per second. And that would be positive. So hopefully you got values close to that. If you didn't, here's how I figured it out. The final concentration of H2, the final time was at 100. So we kind of drew a line over here and said that it was going to be about 0.17 molar. Minus the initial concentration, we said was about 0.65. And so those are the numbers I went off of. If yours are a little bit different, that's okay. Because I really kind of estimated it as well. And so as long as you're close to 0.006, a negative 0.006 molar per second, that will be good. And then what we did for HI, we said the final concentration, which occurred right here, was about 1.73, minus the initial concentration at 20 seconds was again 0.65. And so we subtracted that and then put it over the final time minus the initial time, and we got 0.0135 molar per second. Hopefully that's what you got. Okay, so here's what the actual answers were. And again, we have to be somewhere close to that. So the H2 was a negative 0.00625. And we got 0.006. So we were very, very close to that. And HI the rate there we were very close to as well. So as long as we're close on those, you will get credit. All right, now let's move to instantaneous rate. Let's go through an example problem. This, again, is not in your notes, but it's an example problem of how to find an instantaneous rate. So it says to calculate the instantaneous rate for both H2 disappearance and HI appearance at this time period. So time is equal to 50 seconds. So let's go ahead and find 50 seconds down here between 40 and 60. And so we're looking at the instantaneous rate right there. And at 50 seconds for our product is going to be right there. Okay, so let me go through how I would do this. So again, I like to write down the rate equation. Rate is equal to the change in molarity over change in time. And my units will be molarity, and since my time is measured in this problem in seconds, it's going to be in molarity per second. Now remember what the delta sign means. This delta sign means final minus initial. And so that's what we're going to do. Now, instantaneous rates are quite a bit more complicated, and here's why. We need to take the slope of this line at these points, at just a specific point in time. And it's very difficult to take the slope of a curved line. In fact, you would need calculus in order to do that. And since we don't know calculus yet, and it's beyond the scope of this class, here's a quick and easy way of figuring that out. We need to draw a tangent line. So hopefully in your math class you've gone over what a tangent line is. But let me see if I can demonstrate what a tangent line is. If I have a circle, okay, and I wanted a point tangent on that circle to this point, well, I would draw a line that's a straight line that would be touching the circle at just that point in time. Again, if I wanted to draw a tangent line, say, right here, what I would do is draw a straight line touching that circle at just that point. And so a tangent line touches a curved line at one point. And hopefully it's that point we're looking at. So what we will do, it wants it for both H2 appearance and for HI, or H2 disappearance and HI appearance. And so let's do that again. For H2, let's do that one first. H2, since it's a reactant, is going to be disappearing. It's this green line here. And so if we want to find the instantaneous rate at this point, we draw a tangent line. And I've already done that with this black line here. Okay, this black line touches that green line at that one point, which corresponds to 50 seconds. And so I've kind of already done the math here. But if you take this black line, we're going to take and find the change in concentration for this black line. Now it looks here like my molarity was about right here, and at the start of that line was about right here. Okay, if we subtract those two numbers, I've already done that for you. If we subtract those two numbers, we get a negative 0.28. Okay, and we're going to divide the change in concentration by change in time. Now, my change in time is going to be from the end of this black line, so it looks like about 70 seconds, and the initial at the start of this black line, which looks like about 30 seconds. So 70 minus 30 is going to be 40 seconds. And so that's how I would calculate the instantaneous rate for H2. So if I get a calculator, negative 0.28, and divide that by 40, I get this. It's a negative 0.007. Again, my units, molarity per second. Okay, now let's do it for HI, and because HI is a product, it's going to be appearing over time. And so what I've done is draw that point there at 50 seconds. Now I drew my tangent line, which is this black line. And so that's the line that we're going to use. If you look at the change in concentration, we're up here somewhere, final, and then initial concentration, we're right here somewhere. So I've already calculated, we rose 0.56 molar. And my change in time, I've already calculated it for us, is 40 seconds. So 40 comes down here. Now if we have a calculator, 0.56 divided by 40 is going to be 0.014. And again, my units are going to be molar per second. And so if we look at that and see how close we were, 0.007, and that's negative, so we were correct on the first one, and the last one we were right on as well. Okay, so that's an example problem, a little bit more complex because of the tangent line that you have to draw there. What I've got now is practice problem number 2. And because it's so much more complex, I would like to go through this one with you. So please stay with me as we go through this practice problem. It says to calculate the instantaneous rate for both H2 disappearance and HI appearance at this time point. Time is 10 seconds. So let's go ahead and find that time point. Between 0 and 20 is 10 seconds. So we're going to find it here and here. Okay? Now again, you kind of have to estimate a tangent line, but this curve, if we estimated a tangent line, maybe that tangent line looks like this. Okay, so it's a straight line that touches that curve at that point. Let's do the other one since we're right here as well. We need a tangent line that touches this curve at this point. It looks like it's already pretty much straight anyway, but we know it's going to be slightly above right there and slightly above right there. So those are my tangent lines. So let's start. Rate, write this down, is equal to change in molarity over change in time. So again, we go back to what delta means, final minus initial, and let's do it. So for H2 disappearance, I'm going to say that my final concentration, let's just say that it was about 0.65, so right there somewhere. So 0.65 minus the initial concentration, it's got to be a little bit lower than 1. I'm going to guess like 0.95. This is just a guess right there. But then we're going to divide it by change in time. Well, for the change in time, if we look at the end of this line, we were at 20 seconds. So we're going to do 20 minus the initial time, the start of this red line, is at 0 seconds. Okay? So let's put a calculator to that. So 0.65 minus 0.95, and then divide that by 20. And so here's what I got. The rate, the instantaneous rate, would be a negative 0.015. And again, my units are going to be molar per second. Okay, now let's do HI together as well. So let's do the appearance of HI, which again is this yellow line here. We're trying to figure it out at 10 seconds. So we drew our tangent line already. So again, we're going back to this rate equation, change in molarity. So if you look at the end of this red line, it's about at 0.65. So 0.65 molar is where it ended up, minus the initial concentration. This red line had to be above that yellow line slightly, so I'm going to say maybe it's 0.05. Okay, 0.05 maybe. Yeah, that could work. Divided by the change in time. Now, the final time here was at 20 seconds. So I'm going to put 20 right there. The initial time was at 0 seconds. And so that's how I would calculate it. Let's get a calculator, 0.65 minus 0.05, and then divide it by 20. And so I get that HI is appearing at that time period at 0.03 molar per second. Okay. And so, again, those are kind of approximations. If you get something close to that, I would say that's probably good. That is how you calculate an instantaneous rate. Kind of a little more complicated in drawing the tangent lines, but hopefully that makes sense, guys. I just wanted to quickly, with this video, hopefully understand a little bit better about what a reaction rate is, okay? Please remember this equation here. So the reaction rate is equal to the change in concentration divided by change in time. If you get a graph, concentration is on the y and time is on the x, we're finding the slope of that line, and that will tell us the rate. So anyway, hopefully that's a good introduction to reaction rates, how we calculate them, and hopefully that helped.